Hello, everyone. My name is Rhea Zwani. I am a PhD student at Dublin City University, and I'm just so excited to be presenting at the Forge this morning. I hope you like my talk. So until recently, crystal structures were known to be hard and brittle, but a number of reported cases that show novel mechanical behavior such as bending and twisting have challenged this view. Keeping that in mind, in the next 15 minutes or so, I hope to cover the importance of mechanical and elastic properties of pharmaceutically relevant solid forms or crystal structures. And I'd like to show how these properties can be linked back to structure, which is a key aspect in the grand challenge of engineering new solid forms or crystal structures. I would also like to show how first principles and first principle based methods and techniques allow us to do this. And lastly, I would like to briefly address the relevance of twisting and bending crystals. But what are mechanical properties anyways? So mechanical properties contain extensive information about how a material responds to external stress. The novel mechanical behavior like twisting, bending, and shearing, which is a type of slip or sliding of crystallographic planes undergone usually by layered crystal structures, are of interest in drug development, as they govern bulk properties of a drug substance, such as crystal plasticity. In turn, the plasticity of a drug substance influences how tabletable it is. It is not so much that a crystal can bend or twist or shear, but rather the effect of the deformation on the bulk properties. The mechanical properties themselves are governed by a number of factors that include the crystal packing arrangement of the crystal structure, and most importantly, the types of atoms and molecules in the crystal structure. The types of atoms and molecules will then determine the types and strengths of the intermolecular interactions between them. And more interestingly, the directionality of these intermolecular interactions is also important and can be characterized by structural anisotropy. A good example of where mechanical behavior can neatly translate to structure is the case of paracetamol. So the two polymorphic forms of paracetamol, form 1 and form 2, show quite different crystal packing arrangements and therefore mechanical behavior. The thermodynamically stable form 1 shows these hydrogen bonded pleated sheets as shown by the image on the left, and the metastable form 2 has parallel hydrogen bonded layers as shown by the image on the right. The layered structure of form 2 facilitates slip via shearing, which then results in improved compaction properties and tabletability properties. And this is shown by the image here on the bottom right, where the first tablet is that of form 1. And as you can see, form 1 struggles to form a tablet. The second tablet is that of a stable multi-component crystal of form 2, and it is able to form a perfect tablet. The layered structure of form 2, though, only provides a tentative explanation for the improved compaction properties that we see. And to further explore the relationship between crystal packing and mechanical behavior, computational methods can be adopted. Even more so because experimentally determining elastic properties can be difficult at times. For example, the requirement of specially grown crystals and long preparation times poses a limitation. And in certain instances, experiments can even offer limited information, like with nanoindentation, where information can only be obtained on certain crystal faces. In certain cases, it is even impossible to obtain elastic properties, such as in high pressure and high temperature systems, and also metastable systems. So employing computational methods can allow us to model and extensively characterize mechanical behavior. But in choosing the appropriate computational method, there needs to be a balance between accuracy and cost. Density functional theory, or DFT, is a widely used state-of-the-art ab initio method adopted even in industry. Ab initio in this case means that the method requires no empirical information about the chemical system. There are also limited studies of elastic constants from which elastic properties are determined of molecular crystals using DFT. Although DFT balances accuracy and cost really well, it can quickly become expensive when the size of the system increases. In that case, considering cheaper DFT surrogates that do not compromise on accuracy is a reasonable endeavor. The semi-empirical density functional tight binding method, or DFTB, is one such method. DFTB is itself based on the mathematical principles of DFT, but it is considerably faster than DFT, and it is also untested for elastic constants, which then provides an opportunity to new insights. But before we get into how each method performs, it is worthwhile to mention that the elastic properties are determined from elastic constants, which are themselves components of the stiffness matrix and second derivatives of energy with respect to strain. Essentially, when we compute elastic properties, we actually compute the stiffness matrix. And from the elastic constants, properties such as the shear modulus, the Young's modulus, and less relevant to this talk, the bulk modulus can be determined. The shear modulus can provide insight on crystal plasticity, as mentioned previously, whereas the Young's modulus characterizes the tendency of a material or crystal structure to deform along a single axis, and it can be obtained from nanoindentation experiments and used for comparison reasons. The bulk modulus characterizes the incompressibility of a material. Moving forward, you will hear a lot about the Young's modulus. Moving on, I'll start off with how DFT and DFTB perform when determining elastic properties. But I'd also like to note that elastic properties are determined at 0 Kelvin, void of any temperature and 0 point effects. And the consequences of that will be seen shortly. The 3D spherical plots shown here represent the Young's modulus of aspirin 1. And the values in the table here give the average value of the Young's modulus in gigapascals. What is apparent is that the two computational methods overestimate the Young's modulus as a result of missing temperature effects, with DFT unsurprisingly being close to experiment. Overall, though, the two computational methods capture the Young's modulus well qualitatively. To further explore this qualitative agreement, we can take a slice of the 3D object of the Young's modulus in different directions or planes to give a 2D spatial dependence of the Young's modulus. So I've taken a slice in the AB, AC, and BC crystallographic planes, as shown by the 2D plots here on the bottom panel. From this, we can see that the two computational methods qualitatively agree with experiment, with slight discrepancies. Regardless of the quantitative accuracy, though, the mechanical behavior of a crystal can still be linked to structural features. A good archetypical model is urea. It features only a single type of intermolecular interactions, but it is not an active pharmaceutical ingredient. The crystal structure of urea is composed of planar molecules arranged in a head-to-tail fashion or tapes along the crystallographic C direction, as shown in the image here. The tapes are held together by a strong network of hydrogen bonds, And the network also extends in the orthogonal direction out of the screen. The result is that urea looks the same in two orthogonal directions, which are the AC and BC planes. That also means that urea shows the same mechanical behavior in the AC and BC planes, as shown by the 2D spatial dependence of Young's modulus. The largest resistance of the Young's modulus is in the C direction, and it coincides with the infinite tapes of urea extending in this direction. On the right, from the AB plane, the cross-like arrangement of the NHO hydrogen bonds is reflected by the cross-like shape of the Young's modulus. More so, the stiffest direction of the Young's modulus in all three planes corresponds to the direction of the hydrogen bonds, suggesting that the hydrogen bonds confer extended strength to the Young's modulus. Another aspect that is useful for purposes of establishing structural property relationships is to compare the mechanical behavior of two polymorphic forms. In this case, it's two polymorphic forms of aspirin. And to just see how differences in the structure influences the mechanical behavior that comes about. The two polymorphs of aspirin feature very similar structural properties. They both have a centrosymmetric carboxylic acid dimer, but they vary in the arrangement of these dimers and the resultant interlayer interactions. The distinction between the two polymorphs is seen with the arrangement of the interlayer CHO contacts. Form 1 shows the stimeric arrangement of CHO interactions as shown by the image on the left, while Form 2 shows this catameric arrangement which extends infinitely in one dimension, as shown by the image on the right. The result of some of these structural differences is that the Young's modulus of aspirin 1 has 4 local maxima or lobes, and aspirin 2 has only 6, a distinction that would otherwise be missed, and a highlight really of just how different the mechanical behavior of the two polymorphic forms of crystal structures can be. Like with urea, we can look at the arrangement of the intermolecular interactions in a certain plane. What is shown here is the arrangement of the intermolecular interactions in the AB plane, overlaid with the Young's modulus in the same plane for aspirin Form 1 and Form 2. The interactions include hydrogen bonds holding the diamonds together and the CHO contacts between the layers. The arrangement of these interactions form a butterfly-like shape, which mirrors the shape of the Young's modulus. More so, the directions of the interactions coincide with the direction of the largest resistance of the Young's modulus, suggesting once again that the hydrogen bond confers extended strength to the Young's modulus. In the case of aspirin and urea, the intermolecular interactions and their directionality seems to play a key role in the mechanical behavior, a major step for the successful development and crystallization of functional pharmaceutical solid forms. With that, I would like to close with some final remarks. Firstly, that we are able to extensively characterize the mechanical behavior of an active pharmaceutical ingredient using accurate but relatively cheap computational methods while affording time efficiency. And this extensive characterization makes it easy to link structure to mechanical response. For example, being able to get the spatial dependence of a Young's modulus from any direction has allowed us to see how intermolecular interactions strongly coincides with mechanical behavior. These relations can be logged to be used for crystal engineering of new active pharmaceutical ingredients. Lastly, current standard computational methods overestimate elastic properties because of some of the missing physics in the approximations of computational methods. But there is still excellent qualitative agreement as seen for aspirin. and structured property relations can still be established. In general, this agreement is always useful for some kind of computational screening in the initial stages of a study where more accurate protocols can later be considered. With that, I would like to thank everyone for their attention, and I will be available for any questions. Thank you.